Welcome back to part 2. Calculator is charged, and I have found out what to do for this problem. So, for this problem, we are given that the height of the building is equal to 30 feet. And we also are given that V is equal to 136 miles per hour. With this, now we can, I'll just go back through the QZ thing actually relates to QH, I believe, which is strange because in all of the books and in the lecture notes it says QZ, but if you look at actually using the work, it only relates to QH and actually has nothing to do with QZ at all. So I'm going to replace QZ here with QH. It's definitely wrong, but you'll see what I mean in a second. And as you remember, it's 0.00256, and it's going to be KZ, KZT, KD, KEV squared, but we don't need to do any of those because most of them turn into 1. All we need to know is this is actually going to be KZ on open, flat, level terrain with no obstacles and a direct wind load. It's going to be KZ V squared. And from that table, or not even from the table, yeah, I guess it is from the table. Let me pull that up again. Actually, it's right here. So as you see, the height that we have for the building is 30. So this is actually where we get our KZ from, right here, 0.98. So KZ equals 0.98 at 30 feet. All right, splendid. Now, when we plug this in, QH is going to be 0.00256 times 0.98 V squared. Actually, right here, this KZ yeah, let's see what happens. Times V squared, 136 squared. Okay. So QH is going to be equal to 46.4. I forget what the units here would be. PSF, I believe. Okay. So now that we know this, we can actually make a table, which is what helped me out doing this in the homework, is this table. I don't know where this table comes from, but it looks like this. We're going to have Z here, and it's going to be 0 to 15, just like it asks, 20, 25, and 30. I think this is all of the questions it asks for this. Now we're going to add KZ here. We're going to add QZ here. And P. This is going to be where our calculations really are. So our KZ for 0 to 15, if we go back through to here, it's going to be 0.85, 0.9, 0.94, 0.98. 0.85, 0.9, 0.94, and then 0.98. So this is our KZ for all of these Z values. What's our QZ? Our QZ QZ should equal QH. But I'm actually getting a slightly different QZ in this. So if I do this right here, and I replace this with 0.85, let's say this is correct. And I do this times 0.85 times, oh, goodness me, times 0.85 times 0.8. Okay. That's looking good. And then this times 0.9. Must have been a coincidence. Unless okay. 40 47.349 times 0.85. No. Where does QZ come from? Is it 0 to 15? Let's see. 0.00256 times 0.85, 136 squared. It's not that. Definitely not that. Unless we're doing this here times 0.85 times 0.8, 27. No, we don't do it that way. QZ. By golly, what the heck is QZ? This is all P systems, Q systems, virtual systems. I've just got to figure out what this darned QZ is. Oh man. And I'd like to figure it out fast. It's a brand new one. It's blank. I'm going to keep that out. This is all much later, so it wouldn't have that stuff in it. But this tells me right here, QZ. The height of 30 feet, KZ is QZ equation do we do? Is it that simple? It's that simple. Oh my gosh. So QZ is 46.4 that we got. Do this times 0.85. Here we have 39.44. If we do this times 0.9, 41.76. Similarly, 0.94, 43.61, and 0.98, 45.47. And then right here, I'm gonna make sure that I mention this. QZ equals QH times KZ. Wow, what a revelation. This isn't taught anywhere in the notes. This isn't taught anywhere in the book. Goodness. This is why practically solving these examples is just completely different than theoretically solving them. Wow. Okay. Now we can actually solve these. So it's going to start with a 0.85 right here for all of these. And why does it start with a 0.85 here? Well, because our equation P here, do I have it up anywhere? Yeah, P equals QZ times G times the pressure coefficient minus QH times GCPI. We know this right here. It's going to be plus minus 0.18. Yeah. We know this right here. Here, this one's going to be 0.8. This one's going to be 0.85. So, yeah. And because we know that QH is this, we can just solve for this entire thing here. So if I just do 46, whatever this 46.4 is, and I do this times 0.18, then I know that this is actually plus minus 8.35. So that simplifies this whole thing right here. And we know these two, so we also know what the next step right here is just going to be 0.8 for all of these. Now we can plug in our actual values here for QZ. And then plus minus our 8.35. We have two answers here. So 0.85 times 0.8 times 39.44. We're going to add to this. We're getting 35, and then we're going to subtract. We're going to get 18.4. And let's check. All right. It looks like it wants 19 and 35.7. I'm just going to say all the rounding I'm doing that this one's good. Next one is going to be 0.85 times 0.8 times 41.76 plus 8.35, 36. Oh, come on, server error, really? Session unrecognized, come on. Pearson's such a good for nothing. Just write this down. About 37. And then this minus 8.35, about 20. Problem 5? No. 4 maybe? Yeah. About 37 and 20. So that's good. And similarly, if we keep doing this, we're going to get 38, 21, which is good. And then we're going to get 39 and 23, which is also good. So this equation right here and this equation right here are what you need to know for windward walls. And this is Q4. Let's move on to Q5. Given V equals 137 mph, H equals 14 foot, KE equals 1, fully enclosed, side wall of a building, roof is essentially flat. Okay, and we've got our little table here, but all we really need to know is it's between 0 and 15, which means that KZ is equal to 0.85. And using the equation earlier, QH is going to be equal to 0.00256 KZV squared. QH is going to equal 0.00256 times 0.85 times 137 squared, 40.84. What was this, PSF? I remember. And then our other equation here is going to be P equals Q. Is it just regular Q? QZ. I think this should just be Q. QZ or QH. This is going to change depending on if it's windward wall or not windward wall. And I believe that this should equal QH for all walls that are not windward. GCP plus minus QH GCPI. So P is going to equal 40.84 minus 0.85 times, or should this be times? This is times, not minus, sorry. So I should just do that. And then this is going to be 0.85 again. And this is going to be plus or minus whatever this comes out to be, because this is plus or minus 0.18. We know what QH is right here. So if I do this times 0.18, we know that this is going to be plus or minus 7.35. So the answers we're going to get here are going to be this times 0.85 times 0.85 plus this. Ooh, something's wrong. Hmm. Actually, we don't know what this one is. I'll have to check the book. Is it 0.7? That would make that 31.6. They want 31.7, and then if I do this minus this 16.9. Yeah, okay. So P equals 31.6, 16.9, and wants a negative for these. Why does it want a negative? I'm actually not sure. Oh, back of the building. That's why. It's negative because it's the back of the building. But there you go. So this is actually 0.7. And we know this because if we go to loads part of the book and then we go down to wind loads, they say that for sidewalls, CP is actually negative 0.7. So that's why they're negative. Okay, negative 0.7. And only for the windward wall is it a positive 0.8. Everything else seems to be negative. Leeward wall has a bunch of different values, but for sidewalls, all the values are this. Okay. Wonderful, wonderful. Question 6. Side again. 105 mph. H equals 14 foot. Linear interpolation to determine QH and CP. Okay. So we actually did some of the linear interpolation in this, in the lecture notes. So it wants to know, not even estimate, they want to know what is. We also know KE equals 1. Windward pressure acting on the windward side of the roof. Ooh, this one's a roof one. Okay, okay. I swear we might have actually done one problem with a roof. Yeah. Okay. This one's the most challenging of all the wind load ones, so. This is where the table comes from right here. How do we find I don't think there's any linear interpolation I can get, actually. I think KZ is just going to be 0.85 because from 0 to 15 it's just 0.85. That's interesting. I'm just going to keep on going with the problem then. Let's do this little table here. Z, 0 to 15, 20, 30, oh, here we go. So we actually have a structure. I didn't scroll down enough to see that. So here's what the structure looks like. Essentially, we got this long building here, and it's got this roof, and this is a 10-degree angle. The base here is 50. The height here is h, which is equal to 14 foot. I want to know essentially what this distance here is, and then the centroid of this should be, I think, only a third up. It wouldn't be halfway. It would be nice if it was halfway up the roof. But I think it's going to be a third up the roof. So how do we find this? Well, this is essentially right here. You could think of this as a right-angled triangle of 25 here. We want to know what this height is here. So if we know this, we can do tan, which is opposite over adjacent. We know the adjacent equals 25. We know tan is 10 degrees. So if we multiply this times 25, we should get the opposite angle. So tan of 10 degrees times 25. So this is actually going to be 4.408. Divide this by 3. We're going to add this 14 plus this, which is going to be 15.469 is our QZ, I guess. I don't know if that would actually be our QZ, but this is just going to be our maximum height to the centroid here. Okay, now that we got that all out of the way, actually I think what we want to do is between these two, 0 to 15 and 20, we want to put that number right there, 15.46, 20 and 30. I don't even think we need to do the 20 and 30, but we'll see. And this is where linear interpolation actually comes into play. So we know that for 0 to 15, it's going to be 0.85, and then for 20, it's going to be 0.9. So what's this linear interpolation going to look like? Okay, so we're going to have 20 minus 15 equals 15.46 minus 15. And the values for each of these is going to be KZ. It's going to be minus 0.85. This is going to be minus 0.85. And this is going to be 0.9. So multiplying, let's see what this is over here actually really quick. 0.9 minus I think it's 0.85. All over 20 minus 15. So this whole thing is 0.01. And then we're going to have 15 right here. Just grab it from here. This minus 15. We have this number, multiply those two. So now we've got 0.004 is going to be equal to KZ minus 0.85. So let's add 0.85 to both sides, and we get KZ equals 0.85 pretty much, just about the same, which makes sense if this is only 15.4 instead of 15. It's only going to be a slightly higher kz as well. So let's write that down. 0.85, 0.855, 0.9, and 30 was point, 0.98. Okay, that's our kz values. And then what's next here? QZ. We're going to get this by saying that QH is going to be equal to 0.00256 KZ V squared. I believe that was the right equation. Which means that QH is going to be equal to 0.00256 H equals 14, therefore KZ equals 0.85. So multiply that by 0.85 and then 105 squared, 23.99. Now do this number here times 0.85, 20.39, and then this number here times our new KZ value here, which is going to be 20.5. Then our little value here times 0.9, and then times 0.98. I don't think we need to do this last part, but I don't know. And then remember our equation here, P equals Q, I want to say QH for this. Is it for the windward wall? Leeward, windward. All right, they want it for all different kinds of walls. So I'm going to say Q for now then. Times G, pressure coefficient, QH, GCPI. And we can calculate this one off the bat. This actually should be, no, it's minus this, but it's plus or minus. Plus minus. We know our QH. Let's do this times 0.18 plus or minus 4.32. Okay, now doing this, we're going to have, I believe this is just going to be 0.8, but now for the windward wall, what was the value for the windward wall? For windward wall, this is also 0.8. So let's do this value here. Let's see. Yep. Times 0.8 times 0.8. And now let's add 4.3. No, something's wrong. What's wrong here? Oh, they probably want us to use this one. Nope. This is windward roof. It's actually not going to be 0.8. What was the windward roof one? H over L. Height to the centroid is going to be that 15 right here, divided by the length of 50. 0.3. So it's actually going to be windward angle 10 degrees. Point 0.7. $15.8. Okay. So for this one right here, we're actually going to have, I think this is the only value we need to worry about. So for the windward wall, for this, I got a pretty close answer. Should be negative 15.7. I got 15.8. So for this, I did 20.5 times 0.8 times negative 0.7, and then did plus 4.32, 15.8 negative, and now it's asking for the same thing for the leeward side of the roof. So I believe I'm going to do this minus just 7.16. Ooh, that's not quite. It's close. It's close. It is pretty close. So for this one, I'm getting negative 7.16. They want 7.43. And then the second term in the equation, 1 through 3, internal pressure of the building. Oh, so yeah, this is just, it looks like this is a bit off because this should be 0.438. I got 0.432. So this should just be equal to this right here. So 4.32. It should actually be 4.38. I was a little bit off. I wonder if I did my linear interpolation wrong. Still, it's pretty close. I'm gonna give this one like one of these things. Not a smiley one, but like a straight face, like you know, like I might have linearly interpolated wrong. Maybe I needed to take it to the middle of the roof, not to the third of the roof. So now we're on question 7. This is one of them L over B problems. Tributary area. Yes. So far, just to like very, very briefly go over this, we've talked about live loads, pretty much just wind. Dead loads, just weight. And now we're going to go over tributary area. So this is just chapter 1, homework, I could say number 1. There. So we've gone over all these concepts, and we're almost at the home stretch here for this one. This is 7 out of 9. Question 7. So let's see what we're given. Slab is 225 millimeter thick. And we are also told A and B are equal to 3 meters and 8 meters. And we have this figure, looks like this. There, looks like this. Okay, but this whole thing here is like a concrete slab. This is just like a girder piece. So, yeah. What are we asked? So it wants to know what the correct loading is that acts on member BE, this member here. And let's see, how do we calculate this? So tributary area is just going to be like the area around this where the load would actually be acting upon it. So we know what A is equal to. We know that the tributary area here is going to be this half and this half right here. So this right here, this distance, is going to be 1/2 A, and so is this distance here. So you add them together, and this whole tributary area distance is going to be equal to A. But I guess the first thing is we want to know what the L over B is. So let's do L over B, which is, I believe, this right here is, which one's the L, which one's the B? This one's going to be the L. And I think the tributary area width is going to be the B. I don't know that for sure. I think that's what it is. So this is going to be equal to 8 over 3, 2.66, and that means that the L over B is greater than 2, which means that this is going to be, I think it means it's either, yes, oh yes, so yes, this is a normal, I don't know if it's one way or two way, but it's like a normal system. I think it means it's a one-way system. Okay. Okay. Now from here, what's the weight acting upon this? We know the thickness of the slab. Are we told that the slab is concrete? If we're told it's stone concrete, so this is going to be like what? 0.225 in meters, 225 millimeters to meters. Yeah, 0.225. And now what's the weight of concrete? I think it's 144 pounds per foot. Is that in meters? Like 43? Maybe? It's gonna be like horribly, hilariously wrong. stone concrete is 22.6. We know that WC is going to be equal to rho C times thickness times B, and this capital B, I think this might actually be what they call tributary area. I said as lowercase b, I think it's actually capital B. So WC is going to be equal to, let's see, this is, I think this is weight, not, I'll put 22.6 here anyway, times 0.225, times what's the tributary area? It's actually equal to A, which is 3 meters, times 3. So 22.6 times 0.225 times 3. Okay. No, not quite. Something's wrong here. Density of concrete. What is the density of concrete? This is 150 pounds per foot. Kilonewtons per meter. Times meter. Tributary width, I'm sure B is equal to 3, but that's 3 meters. Thickness is in meters, and it's kilonewtons per meter cubed. Pounds per foot. This is in pounds per foot squared. Where is there anything that's just in pounds per foot? Like it's all squared there. It's all live load. Per foot cubed. That is what we want. Okay, so never mind. We do want that. Times. We did the correct conversion there. That is correct tributary area. Nothing about this is wrong. What's tributary width is B. We know that tributary width B equals 1/2 A plus 1/2 A equals 3 meters. So that's our tributary width. Our thickness, we're told, is at 225 or 275? Could that be the difference maker? It's 225. I put 225 in. And concrete, we know, is 22.6 kilonewtons per meter cubed. So we should actually be left with kilonewtons. No, this is going to be meters squared, meters squared. Should it be the, no, it shouldn't be meters. Meters. So it should be kilonewtons per meter. Man. It says stone concrete. Used for an office lobby. Does that mean anything? That's for live load. Office lobby. They're saying that I mean, it has to be used for something, so 4.79. Do I do this number plus 4.79? Which is 20? Because that's still not right. Hmm. Wow. Yeah, this is... Let me see where I messed up here. We gotta do dead load plus live load. Oh, the live load right here has to be times 3 meters, probably? 4.79 times 3. When I add those up, it's going to be too much, right? No, that is the answer. Okay, okay. All right, I got it. So this is, for office buildings, the live load is going to be this. It's going to be 4.79 kilonewtons per meter squared. And we have this in kilonewtons per meter. This is going to be our dead load. Our live load is going to be equal to 4.779 kilonewtons per meter squared times 3 meters, which is going to be equal to 14.37 kilonewtons per meter. And then if we do dead load plus live load, it's going to be 15.25 plus 14.37 equals 29.6 kilonewtons per meter. There we go. And this is on beam BE. So to sketch this, because it also asks us to like pick the sketch, there's the beam, and the load's gonna look like that, I believe. Is that right? No, no, no. It's uniform, uniform, uniform. Ah, it is a uniform load, which makes sense. It's just concrete. Just even distribution. There. That's W1. This is W1. And now for part 2, what's the loading look like for this? We can see this load right here. We can express this. This was the structure. We could actually make this a point load right here with the equivalent kilonewtons per meter over this many meters. And then these supports right here, this is P, this is 1/2 P on each support. That's how we could just break that up. Like that. And this is on FED. So actually, yeah. Interesting. This is what it would look like this way, and here this is what it would look like that way. This member, and then that one. That's this question done. I did not feel happy about my understanding about this. I mean, it was alright. This whole part was good, but this office building stuff tripped me up. I should have seen it, the load plus live load thing coming. Alright, it's been an hour, small break. Just like take 5 people. We'll be right back into this, and I'll do the last 2 questions. All right, good break. Let's see, what is this? Question 8. Like the same thing. Same, basic concept, except for A equals 4 and B equals 5. So now, if we just briefly look at this here, kind of looks like that. 4, 4, 5. Tributary area is still going to be here, which means that B equals A equals 4, and then B over L equals 4 over 5 is going to be equal to, I don't actually know what 4 over 5 is, 0.8, which is, I think, which means this is going to be, sorry, L over B, 5 over 4. 1.25. If it's less than 2, that means it's a two-way system, and we're going to have something that looks a little bit more like this. Where these all come from 45-degree angles, and yeah, this is going to be, so say that this is AB, then AB would look like this for distributed load. So yeah, moving on now. It wants to know BE, which actually is this is B, this is E, so we already know what this is going to be ahead of time. It's kind of funny. Yeah, so it's going to be pulling from like the corners like here, I guess is what it would look like. But regardless, we know that the thickness is 0.25 this time. Remember our WC from last time, WC is going to be equal to rho C T times B, which is going to be equal to, it's still stone concrete, still an office lobby, so we're still going to have 4.79 kilonewtons per meter squared, times what's the tributary area, B is 4, so 4.79 times 4, which is going to be 19.16, and this right here is going to be, oh gosh, what was it last time? 22.6, I want to say. Times 0.25 times 4. Equals 22.6. Oh yeah, that makes sense because these cancel out. So now we have this plus this. And this is the dead load, this is the live load. Dead load plus live load equals 22.6 plus 19.16 equals 41.76 or 41.8 kilonewtons per meter. And this is correct right here, speed round, and this is what that looks like. This is going to be split up like this. 2 meter, 1 meter, 2 meter. And right here is our W1. W1 equals, and now it's asking us also what FED would look like. And remember, this is FED. This one is going to be our BE. So this is BE. FED. Oh yeah, it would look a little bit funky, wouldn't it? FED would look like this. With P here, P over 2 here, and P over 2 here. This P is going to be, I believe, this weight here. And because of the tributary area being a triangle here, we're going to have these triangles here, and these would be the supports. It's going down against the supports. Interesting. I'll have to look further into how this works. I knew how to get to this at some point. I could probably learn it again pretty quick. So tributary area as a concept I can come back to. I get the broad strokes, but mostly these graphs here, I kind of rushed through them, but I know to come back to, if I have extra time, come back to tributary area. These. Let me see if I can think about it real quick. So yeah, we're gonna have all the load here, P, and these triangles must come from it just being a two-way system. I don't know if I ever uploaded video on tributary area, but if I did, then I should rewatch them. Question 9. Last question. I think this one's tricky. Same thing, kind of. So question 9. Given 4-inch stone concrete slab, live load equals 460 pounds per foot squared, A equals 6, B equals 18 foot. We know that stone concrete is 144 pounds per foot cubed. We can get this 4 inches is actually 4 over 12 foot. Quick conversion there. And tributary area for this concept here, if we just say that's 18, right there that's 6 and 6. Same concrete slab is going to look like that. Tributary area is going to be half of this, 1/2 6, so we're going to say that B equals 6 L over B, right? Let me try to get that. Yeah, L over B equals 18 over 6 equals 3, which is greater than 2. So this is a one-way system. Because this is a one-way system, this should be uniform. Should be the same as the other ones. But let's go through what W1 is here. So what's this going to be? WC is going to be equal to rho C times T times B. Rho C is 144 times thickness is 4 over 12 times B is going to be 6. So this is going to be 288 pound per foot plus the 460 pound per foot here. I'm getting 748 kip foot. 3.06 kilo fudge. Where'd I mess up? Stone concrete slab. Yep, it's the right pounds per footage. Live load we were just given is 460 pounds per foot squared. There it is, 460 pounds per foot squared times 6 foot. There we go. So this 288 is actually plus 2760. It's the same mistake I did earlier. Foot squared times 6 foot. And this is actually going to equal 3048 or 3.05 kip foot. Close enough to 3.06, honestly. And what's this over here going to look like? Same as the other one. We have these supports, except it's actually going downward, which I don't quite understand yet. But this is P over 2, and that's P over 2. So the only thing I really need to work on is this graph here, how that works, which just takes some mental energy, which I will expend when I have more of it. And I don't think this is a very major concept to have like a shaky grasp on. I don't think my final grade will depend on the final part of a tributary area equation, but it might, so I'm just going to remember this, and I'm going to come back to that. And this was chapter 1 for structural engineering. The things that we went over, I'm just going to say DL for dead load, live load, tributary area. So what were the live loads? Wind. Tributary area, one way, two way, and for dead load, pretty much just weight. These are the major concepts, and I'll have to come back through and write the major equations, or just pull the major equations from this, but I could do it right now. I do have some time. So I guess the major equations, really just the wind one had the major ones. It's going to be the QH equation and the P equation. This one had L over B. It's like the only equation you need to know for this one. Pretty much it. And just for this one, and also QZ. And this is going to be 0.00256 kZV squared, and this one's going to be Q times G times CP minus QH GCPI, and QZ is going to be equal to QH times KZ. Those are the major equations here, and this one's just dimensional analysis. Pretty much, I don't think there was anything that we needed to know for that. Also, for this one, W1 equals DL plus LL. All right, that's pretty much it for chapter 1 for structural.